Good morning. All right. Now we're asking about an exam. We're going to have one. Today is the first day of week number 9. Our next exam will be during week number 11, not next week, but the week after. And it will cover chapters 4 and 5. Chapter 4 that we're finishing up this morning and chapter 5 that we're starting this morning. So let me start by asking if anyone have any questions from the homework for chapter 4. Number 42. Good, because that's one of the problems I wanted to... There are 2 problems I wanted to go over with y'all, just as examples to finish up chapter 4. This will cover one of them. A box is given a push so that it slides across the floor. How far will it go before it stops? Given that the coefficient of kinetic friction is 0.15 and that the push imparts an initial speed of 3.5 meters per second. So, well, you've got a box. That is sliding across the floor. Its initial velocity is equal to 3.5 meters per second. And I went and left my calculator in the office, so everybody get your calculators out. I'm going to need you to do the arithmetic. The coefficient of kinetic friction is 0.15. Does everyone notice that at no time does it tell us what the mass of this box is? It's an unknown quantity, but we know it's got to have a mass. And we know that that it is experiencing a force in the negative direction due to friction. And that it has an initial velocity of 3.5 meters per second. We'd also know that the force due to friction is equal to 0.15 times mg, times the normal force. So, let's look at our kinematic equations, see which one might help us. And how many of you have put some kind of marker, a post-it note or something to mark the kinematic equations in your book so you can find them quickly? That'll work too. So, what is the only acceleration this box is going to experience once you give it an initial acceleration in that direction? And it has that initial acceleration gives it this initial velocity. But at that point, what is the only acceleration it experiences? What's the only force that is acting on that box? We know that the gravity is pulling it down and the normal force is pushing it up, and those two cancel out. Let's write it out. The sum of the forces acting on that box equals minus mass times gravity plus mass times gravity minus mass times mu sub k times gravity. And all of this equals the total mass of the box times its net acceleration. Okay, well, these cancel out, plus mg minus mg, so that means we have a net force acting on that box of minus mass times mu sub k times gravity, and that's equal to the mass times the net acceleration. All right? Everybody with me so far? But we can divide out the mass on both sides. We don't need to know the mass to know the acceleration that it's experiencing. We know that its net acceleration is equal to minus mu sub k times gravity, times 9.8 meters per second squared. That's the only acceleration this box is experiencing once you start it sliding across that table. So, we know its initial velocity, and we know the final velocity that we are looking for is when it reaches 0. And we know its acceleration. What we don't know is how far will it go until it stops. So let's look at, we've got a kinematic equation right here that gives us that distance, delta x or x minus x naught, as a variable. So let's write that out. We've got v squared is equal to v sub naught squared plus 2 times a times x minus x naught, or delta x. Well, we know the final velocity we're looking for is 0. We know its initial velocity is 3.5 meters per second. Square that and add 2 times our acceleration is mu sub kg times delta x. Mu sub k is 0.15, so this becomes, somebody give me the 3.5 squared. 12.25 meters squared per second squared plus 2 times 0.15 times 9.8 meters per second squared times delta x. Now, how do we solve this? Just algebraically subtract the, and actually, you'll notice I made a minor sign error here. This acceleration is not mu sub k times g. It's minus mu sub k times g. So let's correct that. And now we can solve for x by adding this to both sides. What's 2 times 0.15 times 9.8? 2.94, add 2.94 times delta x to both sides, and that gives us 12.25 Divide both sides by 2.94. What do we get? Meters. Now let's check our units just to make sure. What do we have here? We have meters squared per second squared, right? Because we had a velocity that we squared. Here we have 2 is unitless. Mu sub k is also unitless. 9.8 is meters per second squared. And delta x is meters. So this is meters squared per second squared. So we're good there so far. We're adding meters squared per second squared. We subtract that from both sides. We divide. This 2.94 is just meters per second squared. So if we divide meters squared per second squared by meters per second squared, that leaves just meters. So our units check out. Everybody see how we got there? And the important step that I really want to impress upon y'all was that initial setup where we did not look and just look at it and intuit what's important and what's not. I went through the entire process of summing up all of the vector forces acting on that box. And that's what I want to. That's the second problem that I wanted to go over with y'all. Would be another example of that very same exercise. And it's the same problem we worked in the lab when you did the dynamics lab. The 2 boxes and a pulley. Except this one I want to go through with you is out of the book. And it incorporates the force due to friction. And I think that informs why it's important to go through the actual process of adding up all of the forces and don't try to just wave your hands around. Don't get off into the hand waving and say, well, this we can look and see that this is all that we're going to need to calculate. Did you bring enough for everybody? Okay. You want to turn in your book to page 96. We're going to look at example 420. Now here you'll recognize the setup. It's 2 boxes with a pulley, the smaller box hanging, and that weight is what accelerates the whole system. And in point of fact, there's nothing wrong with treating the whole thing as a single unit, one single mass that is only being accelerated by the force due to gravity on the smaller box. But the instant you throw in that force due to friction, suddenly that becomes a little bit more complicated and maybe not quite so intuitively obvious. So let's take this a more general and analytical approach to this problem. So we're going to start with a box on a table that has 5.0 kilograms of mass. There's your pulley. And there's your second box of 2 kilograms. Mass B, mass A. Now, we also know the coefficient of kinetic friction between box A and the table is 0.20. Now, let's start by adding up all of the forces on both of these boxes. And we're going to treat them individually. Okay? So here we have the force pulling down is mass times gravity. And we'll call that the positive direction. There's a force pulling up that is equal to the force of tension in the string. Do we know what the force of tension in that string is? Anybody? Since we expect that the box is going to slide, to accelerate and move downward, then we know that the force due to tension must be less than the force due to gravity. But that's all we know about it. At this point, we don't know the magnitude of that force due to tension. So let's look at the box over here, this next box. We have mass times gravity pulling down on the box. We have a normal force of minus mass times gravity pulling up, pushing back up. Here we have the force of tension in the wire, in the string, pulling it horizontally to the right, that we'll call positive. And here we have minus the force due to friction, which is mass A. Yeah, I should have made that clear. That's mass B times gravity. We have mass A times gravity times mu sub k. And that's the force due to friction acting on this second box, on mass A. So let's start by writing out the sum of the forces on both boxes. We know that for box B, we have mass B times 9.8 meters per second squared minus the force due to tension, and that is equal to mass A times the net acceleration of the box, of mass A. We don't know yet what the total acceleration is going to be, and we don't know yet what the force of tension is. But we know they're there, and that algebraically they fit together like this. So now let's look at box A. We know that mass A times gravity, the sum of the forces is mass A times gravity minus mass A times gravity, the normal force. That's the force due to gravity. That's the normal force. Plus the force due to tension in the wire, or in the string, minus the force due to friction. And that is equal to mass B times the net acceleration. So we can immediately start canceling out these. We can rewrite the force of We know the force of tension is there. We don't know what it is. But we can write the force of friction as mass A times mu sub k, which we've got a number for that, so I'm going to put it in. 0.2 times 9.8. So the force of tension minus the force of friction is equal to mass A times the net acceleration. Now, we don't know this value. We don't know this value. But we have two equations that are independent of one another, and we have two unknowns. So we should be able to algebraically solve for those two unknowns. Well, we can immediately solve this one. The force of tension, we can now say that it is equal to mass A times the acceleration of the system plus mass A times 0.20 times 9.8 meters per second squared. Or we can factor out the mass A and write it as mass A times acceleration plus 0.20 times 9.8. That is the force due to tension. So let's replace it up here and rewrite this box B equation as mass B times 9.8 meters per second squared minus the force due to tension, mass A times acceleration plus 0.20 times 9.8. And that is all equal to mass A times the acceleration of the system. Now, and again, I want to make sure you understand, because this string is connecting the two boxes, we know that however much one is accelerated, they both have to be accelerated the same amount. Okay? So this A sub y for this box and A sub x for that box are actually the same acceleration, the same value of A. All right, well, let's see. Here we've got mass B times 9.8 is equal to mass A times A plus 0.20 times 9.8 plus mass A times A, or factor the mass A out of both of these, and we get A plus 0.20 times 9.8 plus another A What's 0.2 times 9.8? Somebody with a calculator. Right. Okay. Now, let's start plugging in these. I've been writing mass A and mass B, but we know what those numbers are. Mass A is 5 kilograms and mass B is 2 kilograms. So this is 2.0 times 9.8 equals 5.0 times 2 times acceleration plus 1.96. And we need to get that 2a on one side by itself, so let's do that. 5 times 2a will just be 10 times a, plus what's 5 times 9, 1.96? 1.96. So it just went back to 9.8? Okay. And that's equal to, what's 2 times 9.8? Hold on, before we do that, because we're going to save us some arithmetic here. Let's subtract 9.8 from both sides, and we end up with 2 times 9.8 minus 1 times 9.8 is equal to 10 times acceleration. Well, 2 minus 1 is pretty easy for me, even for me to do arithmetically. So we have 9.8 is equal to 10.0 times A, and that means we can now solve for A by dividing 9.8 by 10 is, what is that, 0.98? So our acceleration of the whole system is 0.98 meters per second squared. That's not what they got in the book. They got 1.4. Where did I go wrong? Somebody examine this and see if we can figure out where I went wrong. Yeah, I see that. Okay, let's check. First of all, let's check the equations. I got, for box B, mass B times gravity minus force of tension. Okay, that's right. For box A, force of tension minus force of friction. That's right. Now they said force of tension was force of friction plus mass A times acceleration. Well, that's what I got. Oh, wait a minute. Ah, there's where I went wrong. Nobody catches it? Nobody sees it? No, I didn't switch them. I changed mass B to mass A and simplified that equation. Look here. Right here, I was solving I was solving box B equation. And I did that by adding force of tension to both sides. Well, hold on now. Am I confusing myself all over again? Yeah, I am. Because it's when I add the when I'm solving for the force of tension, I add the force of tension to mass A times gravity. Yeah, here's where I messed up. Right here. That is not true. If we're solving this equation for the force of tension, what we have is mass B times 9.8 times G minus Ft is equal to mass A times the acceleration of the system. Now, being careful not to mess up the signs, I got minus Ft is equal to mass A times A minus mass B times G. But the way I wrote it before, I transposed this to mass A and then factored out a mass A where that was not. I shouldn't have done that. So let's scratch all of this and do this correctly, because I don't want to leave y'all with the wrong information about this. Now, we can multiply through by -1 just to make everything a little more easy to work with. We've got force of tension is equal to plus mass B times G minus mass A times A. That is now our force of tension, which we can substitute into this equation. Remember, we solved the box B equation in terms of force of tension. Now we will substitute that force of tension into the box A equation, which is force of tension minus the force of friction is equal to mass B, the big box, times A. And force of tension we now write as mass BG minus mass AA. And from that we subtract the force due to friction, and that will give us mass B times A. Now, the only thing in this equation that we don't know is A, right? We know mass B, we know both of the masses, we know gravity, and we know the force of friction in terms of gravity and mass A, because we know mu sub k. So let's solve this in terms of A. Does everyone understand? We've got the force of friction is just mass A times mu sub k times G. These are all known numbers. So force of friction is not an unknown quantity. So we add mass A times A to both sides, and we get mass B times G minus the force due to friction is equal to mass A times A plus mass B times A, or A times mass A plus mass B. And now we can put in the numbers for mass B times G. Mass B is 2 times G. Minus the force of friction, which is 5 kilograms, times mu sub k, which is 0.2, times 9.8. And that's equal to A times, so somebody do the arithmetic. 2 times 9.8. Okay, 5 times 0.2 times 9.8. That really does work out to 9.8, huh? I guess so, yeah. 5 times 0.2 is 1. Okay. And mass A plus mass B is 7 kilograms. 19.6 minus 9.8 divided by 7.0 gives us A. Somebody do the arithmetic. And please tell me it comes out to 1.4. 1.4 meters per second squared? Yeah? Excellent. So, 2 lessons to take from this. The first and important lesson being that even with a complex system, if you carefully sum all of the forces on every individual component, you can solve for the whole system. All you have to do is reduce it to however many unknown values you're looking to solve for, you need that many independent equations. What does that mean to say you need independent equations? Let me give you a counterexample to maybe make this a little more intuitive for you. You know Ohm's law. Everybody here knows Ohm's law, right? I equals E over R. There are 3 unknowns in that equation. And if you know any 2 of them, you can solve for the 3rd one. In other words, since you have one equation, as long as only one of these quantities is unknown, you can solve for it. But if you want to solve for 3 unknowns, you need 3 equations, right? Okay. Well, if that's true, then it's also true that R equals E over I. And it's also true that E equals I R. 3 equations, 3 unknowns. Can you solve for the 3 unknowns? No. Because even though you have 3 different equations, they are not independent. Any one of them can be derived from either of the other 2. Okay? That's what it's meant when it said you need 3, if you have 3 unknowns, you need 3 independent equations. In other words, 3 separate equations that you cannot derive from each other. They have to be independent. That's how you solve this. Now, of course, the secondary lesson that was completely unintentional and a little bit embarrassing is that when you start doing the math, you have to be careful because it's very easy to make a simple mistake like that, especially when you start dealing with multiple subscripts. And that's all it took, was accidentally rewriting mass B as mass A, and then continuing on down a primrose path until I came up with an answer that was a perfectly good solution, but not the right one. It was a perfectly good solution to a whole different problem. Now, any questions? All right. Any more questions from the homework? All right, well, we got a few sections of Chapter 5 to get through this week. Has anybody read ahead, looked in the book to see what's coming up in Chapter 5? We're going to talk about circular motion, uniform circular motion, or centripetal acceleration. And for the record, I tend to pronounce it centripetal. Others tend to pronounce it centripetal. I don't really care how you pronounce it. Okay? Let's go back and talk about Newton. Who can tell, who remembers what it is that Newton actually accomplished when he wrote his famous 3 laws of motion? And just as a quick refresher, somebody tell me the first of Newton's 3 laws of motion. Law of inertia. A body at rest will stay at rest unless acted upon by an outside force, and a body in motion will stay in motion unless acted upon by an outside force. What's the second law of motion? Force equals ma. But more specifically, seriously, start thinking of it as the sum of the forces is equal to the mass times acceleration. Okay, because there's generally more than one force involved. What's the third law? Well, that's the first one. Every action has an equal and opposite reaction. If the tension in the string is if the tension that the string is exerting on the box is equal to 5 newtons, then the force that the box is exerting on the string is also 5 newtons. And the second law, the sum of the forces is mass times acceleration, is where we introduce the concept of an unbalanced force, a force that is not counteracted by some other force. We did that whole solution of the 2 boxes and the pulley. Can anyone tell me what we just conveniently neglected and overlooked? We assumed that the force of tension in that string, the unbalanced force, we assumed that it was greater than the force of friction and that it led to a net acceleration. Turns out it was greater than the force of friction, of kinetic friction. But if it was not greater than the force due to static friction, then nothing would have moved. That box would have just sat there until somebody came and gave it a bump and got it off of the static friction and into a realm of kinetic friction. Okay, so anyway, back to Newton. What was it that he actually accomplished when he gave us those 3 laws of motion? from the time of the philosophers, before the scientific method was introduced by Galileo, what was the belief? That there were two separate realms with two separate laws of motion. That in the world, on Earth, there was one set of laws of motion. And originally they thought that, that the natural state of all objects was to be at rest. Galileo came along and pointed out that no, the natural state of all laws, of all motion in the terrestrial realm is that the motion will continue that the motion will continue unaccelerated. The natural state is unaccelerated or inertial motion, not to be at rest. And that only friction brings objects that are moving to rest. But even Galileo still accepted that there was this other realm of motion, and that was the celestial realm, the stars and planets, and how did they move? Remember what the word planet means? Wanderer. That's literally the meaning of the word. Planete means wanderer. Because all the other stars moved in fixed positions relative to one another. That's how come they drew constellations, because they knew all of these stars they're going to stay together as one constellation. And they're going to move in this big circle. And then the planets were these wandering stars that came along and they moved in their own independent circle. But the belief was that all motion in the celestial realm, the natural state of motion in the celestial realm, was for everything to move in a perfect circle. This was distinct from what everybody believed about the terrestrial realm, where, thanks to Galileo, they understood, no, the natural state of motion is unaccelerated motion. But the natural state of motion in the celestial realm is still for everything to move in perfect circles. And of course they observed things that contradicted that. They watched planets move and then stop and back up and stop and move again. That's called retrograde motion. And they said, well, how does that happen? And they said, oh, well, you know what? Turns out that the natural state of motion is for everything to move in perfect circles, but sometimes it's little tiny circles moving along a bigger circular path. And sometimes they had to have even little tinier circles moving around those little tiny circles that themselves moved in big, long paths, big, long circular paths. Now that sounds kind of silly to us, right? Except it's not, because that is a perfect description of what you will discover someday if you get into some higher level math courses. It's called a Taylor expansion series. That's it. The Taylor expansion series, which also leads to the Fourier transform, basically says that any arbitrary function you can write, from a square wave to a triangle wave to an arbitrary sound wave, it can all be written as the sum of sine and cosine wave functions. In other words, every arbitrary every arbitrary path you can describe can be written as a sum of little tiny circles moving in bigger circles, moving in bigger circles. Okay? Now, it took Taylor to figure that out mathematically. The philosophers before Galileo and even after Galileo kind of intuited it. But then came Newton. And Newton came along and said, wait a minute. Why should there be separate laws of motion in the celestial realm than in the terrestrial realm? And he didn't know. He couldn't come up with an answer. And then one day, sitting under an apple tree, this is the story you've all heard, he was sitting under an apple tree, an apple dropped and hit him on the head. And it dawned on him, everything is attracted to the ground, to the earth. And he began to think of this invisible force acting on everything, that masses would be attracted to each other in proportions with forces relative to their masses. Okay? This wasn't a new idea. He already knew force was equal to mass times acceleration. And this was the thought experiment that he went through in his mind. He said, suppose I got up on the top of the tallest mountain in the world. Now, I have no idea if he knew about Mount Everest, but he envisioned that at some point there is a highest possible point on the planet. Now, suppose I get there and I throw this apple as hard as I can with as much speed as I can give it. How is it going to fall? He said it's going to fall just like that. And how far, we've worked out the kinematic equations, how far it travels will depend on how much initial velocity I give it. Because now it's going to be accelerated down towards the ground by gravity. And then he said, okay, well, what if I throw it a little bit faster? Well, then it'll go a little bit further before it hits the ground. And then if I throw it even faster than that, it'll go even farther. And it might go all the way beyond the horizon, beyond as far as I can see, before it finally hits the ground. If I throw it even faster than that, it could possibly reach all the way to the other side of the planet before it finally hits the ground, if I throw it fast enough. And he then went on in this mental experiment, this thought exercise, and he envisioned being able to throw it fast enough so that as fast as it fell, as it was accelerated in towards the earth, the curvature of the earth would also fall away. And that if he threw it that fast, it would just keep falling towards the earth at the same rate that the surface of the earth fell away, until it would come all the way back around and hit him in the back of the head. Now, he didn't do the math enough to know that it would take about 90 minutes for it to get around and hit him in the back of the head. But actually, it probably wouldn't take that long, because that's if we actually get up to a low Earth orbit. When John Glenn finally did get up in a rocket ship and actually orbit the Earth, that's what it turns out it took him. It took him about 90 minutes to travel all the way around. Everyone understand this thought process that Newton went through? What he figured out was that as long as gravity is always pointing directly straight down towards the center of the earth, if you're going fast enough, your natural motion will not be parabolic. If you get that fast, your natural motion will then become circular, just like in the celestial realm. And that's when it dawned on him that he had just unified the natural motion in the terrestrial realm with natural motion in the celestial realm. And he did it by coming up with the concept of centripetal, or centripetal literally means center pointing, or pointing to the center. That by coming up with this notion of centripetal acceleration, by understanding that that's what gravity produces, he unified both realms of motion into one universal law of motion, and what he would introduce as the universal gravitational constant. See y'all on Wednesday.